Well, let's take a look at the first one here. See how you're doing on that one, and I'll give you some more time on the other two if you'd like. So for volume and surface area, we start out with volume. The first thing we need to find the volume is the area of the base. Since the base of this is a circle, it's pi times radius squared. What is the radius of this circle? 4, perfect. So pi times 4 squared, which is 50.24 square feet. So then the volume is that area of the base, 50.24 square feet, times the height of 10 feet, or 502.4 cubic feet. For surface area, we have the area of the base, 50.24. In fact, we have it twice because there's one on top as well. Next, we have lateral area. The lateral area requires us to know the perimeter of the base. The perimeter base is just the circumference of a circle, so that'll be pi times that diameter of 8 feet, which is 25.12 feet. So the lateral area is that perimeter of the base, 25.12 feet, times the height of 10 feet, which comes out to be 251.2 square feet. So that's going to give us a total surface area by adding those three numbers up, 351.68 square feet. Any questions on that one? Okay. How many of you are done with number 2? Okay, just a couple of you. I'm going to give you a couple more minutes to work on 2 and 3. We'll talk about them here in just a little bit. Just wanted to make sure you guys were on the right track. Okay, so number 2. First thing we need to do in finding the volume is to find the area of the base. This is a triangle, a right triangle that's 6 by 8. So it's 6 inches by 8 inches divided by 2, or 24 square inches. So then the volume is found by taking that 24 square inches times the height of 15, which gives us 360 cubic inches. Any questions on the volume for that one? Okay, then, so for surface area, we already have the area of the base as 24 inches squared. And there is 2 of them, one on top, one on bottom. To do the perimeter of the base, we need the length of this back side. Well, since that's a right triangle, there's going to be A, B, and C. 6 squared plus 8 squared is going to equal C squared. If you work that out, it comes out to C equals 10 inches. So that perimeter of the base is just 6 plus 8 plus 10, or 24 inches. So our lateral area is that perimeter of the base, the 24 inches, times the height, the 15 inches, which is 360 inches squared. By the way, it's just a coincidence that the lateral area and the volume are the same number. So anyway, we add that up, add those three up, you get a total surface area of 408 inches squared. Any questions there? Okay, then the last one on our cone. Once again, we have to start out finding the volume with finding the area of the base. The area base is a circle, so it's pi times radius. What's the radius of that circle going to be? 8. So pi times 8 squared, which is going to be, what, 200.96 inches squared. Now the volume here is going to be slightly different. The volume is the area of the base times the height of 15 inches. But because it's a cone, it's divided by 3. So that makes it come out to, there you go. Oh, what is that? 1004.8 inches cubed for volume. For surface area, we already have the area of the base. There is only one base, so we're only going to put that in there once. We do need the perimeter of the base. The perimeter of the base is going to be a circumference again. So it'll be pi times that 16-inch diameter, which is going to be 50.24 inches for the perimeter of the base. Since this is a cone, we are not going to use the height for the lateral area. We need to use this dimension right here, which is a slant. And we'll find that slant by making a right triangle. This in the green here is just the height of 15 inches. This is the radius of the circular base, which is just going to be 8 inches. So that slant, if I label these A, B, and C, the slant is the hypotenuse, it'll be side C. So it's 15 squared plus 8 squared equals C squared. If you calculate that out, you will get that that is 17 inches. I'm trusting at this point that you guys can do the A squared plus B squared equals C squared and solve for a missing side. Anybody having any questions or problems with that? Do you want me to go over it? Okay. So we have 17 as our slant. So our lateral area is that perimeter of the base, 50.24, that should have been, 50.24 inches, times that slant, the 17 inches, divided by 2 because it's a triangle. That's going to give us 427.04. That's inches squared. So that's the lateral area. Our total surface area, we're going to add those two numbers together, which is going to give us 628 square inches. is our total surface area. Any questions? Okay, keeping with the geometry, the next thing we're going to talk about today is similar figures. And similar figures are created literally by taking an enlargement or a reduction of another. For example, if I take this triangle here, and I copy it, maybe. So again, let's say we have a triangle here, and we're just going to duplicate it. And I reduce it, I shrink it down. It's still the same shape, it's just been shrunk, it's been reduced. If I know the sides of the original triangle in black over here, oh, come on now. Let's say this is 9 inches, 18 inches, and 21 inches. And this now has become 6 inches here. I want to know what those other sides would become. Now, something very important to point out here. You watched me copy and reduce this, so we know that this side goes with this side, and so on. If we didn't know that, if we didn't watch that happen, what we would actually do, what we use, is the angles. We compare the angles. Even after reducing it, the length of the sides change, but the angles will not. This angle in purple will equal this angle here. This angle here would still be equal to that angle there. And then, of course, the third angle has to be equal. Now, because we know that the angles of a triangle add up to 180 degrees, we only need to know that 2 out of the 3 are the same. But that is the easiest way to tell that 2 triangles are similar, is if the 3 angles are the same, you know the triangles are the same. And as I said, if you know that 2 of them are the same, the third one has to be. To deal with similar figures, and not just triangles, but it can be any shape, we have something called corresponding sides. Corresponding sides are the sides from before and after, the same side from before and after the reduction or the enlargement. In this case, that's the one I have in red on each of them. That would be a corresponding side. The 9 inches corresponds to the 6 inches. I can write that as a ratio. It doesn't matter which one I put on top. I can put the 9 inches over 6 inches or 6 inches over 9 inches, either way. I just have to make sure I stay consistent with that. Now I have to look for another set of corresponding sides. Let's say I want to find x here. First of all, going over to my proportion here, is x going to go on top or bottom in this second ratio? It's going to go on bottom. Why does it go on bottom? Well, because it's from the same triangle as the 6 inches. So it has to match up with the 6 inches. What is the corresponding side in the other triangle? The 18 is the corresponding side. Very good. Notice the 18 inches goes up there. That is from the same triangle as the 9 inches. So you'll notice there are relationships in both directions. The 9 and 18 both come from the same triangle. There's a relationship. Just like the 6 and the x come from the same triangle. Going up and down, these two, the 9 and the 6, are corresponding sides. The 18 and the x are corresponding sides. In every proportion, you have those relationships in both directions. If you can't determine that relationship, then your proportion most likely is not set up correctly. Now, how do we solve for x here? We cross multiply. 6 times 18 is 108, and we divide by the 9, which gives us that x equals 12. So x is 12 inches. Now we are still looking for side y here. We can use the same setup. 9 inches still corresponds to 6 inches. Does the y go on top or bottom? Is it from the triangle that contains the 9 inches or from the triangle that contains the 6 inches? From the 6 inches, so it goes on bottom. So then what's going to go above it? 21 is the corresponding side. So we will cross multiply. 6 times 21 is 126 inches. Divided by 9, which is, what does that come out to be, 14 inches? So y is 14 inches, x is 12 inches. We don't always get them matched up nice and neat like that in the same orientation. Here, these are similar triangles. I guess I should prove that they're similar triangles. Let's say I tell you that this angle and this angle are the same, and this angle here and this angle up here are the same. So if we've got two angles, we know the third angle must be the same. So these are similar triangles. They have the same angles. If I tell you that this side here is 3 inches, this is 9 inches and 12 inches. If I tell you this side over here is 28 inches. To set this up, when I have a figure like this that's missing two sides, I have to find a set of corresponding sides where I know the length from both triangles. Since 28 is the only length I know in this triangle, I have to use the 28. What side corresponds to it from the other one? The 12. The way we know that is the 28 is between those two angles we compared. The 12 is between the same two angles. So they have to be corresponding sides. Now let's say we want to find x first. Is x going to go on top or bottom here? Top, because it's from the same triangle as the 28. And what's its corresponding side from the other figure? The 3 inches. So we can cross multiply and divide. 28 times 3 divided by 12. X is 7, correct? Does that work out? Okay. To find y, we start out with the same relationship. We still have 28 inches corresponds to the 12 inches. Y is going to go top or bottom? Top. It's still from the same figure as the 28. What's going to go below it? 9 is the corresponding side from the other figure. We will cross multiply and divide. 28 times 9 is what, 252? Divided by 12 is 21, I believe. So y is 21 inches. Any questions there? Now, it doesn't have to be triangles. It can have, more than 3 sides. It could look like that. So let's say we've got these two. Let's say I give you this angle and this angle are the same. Those two angles are the same. And those two angles are the same. Had to have 3 out of the 4 angles here because there's 4 sides here. If I label, let's see here. I'm going to call this side here 6 inches. This one's going to be X. I'm going to call this one 10 inches. This is going to be 9 inches. I'm going to call this Y. And I'm going to call this one 12 inches. I'm going to ignore that 4th side on each of them for now. In your notes, I want you to take a couple minutes, try to find X and Y. We'll talk about it in a minute. Okay, so what is our pair of corresponding sides that we know from both figures? 9 and 6, and it doesn't matter which one goes on top. So we'll put the 9 over 6. To find X, where is X going to go, top or bottom? It goes on bottom because it's from the same figure as the 6. What's its corresponding side? Well, it's from the angle with 2 hashes and the angle with 3 hashes. Over here, we got 2 hashes and 3 hashes. The side that's between them is the 12 inches. That's its corresponding side. Cross multiply and divide. 6 times 12 is 72. Divided by 9 is 8 inches. So X is 8 inches. To find Y, we're going to start out with the same thing. 9 compares to 6. Y going to go on top or bottom? It goes on top this time because it's from the same figure as the 9. Its corresponding side from the other triangle is 10 inches. We're going to cross multiply and divide. 9 times 10 is 90. Divided by 6 is 15 inches. So Y is 15 inches. How many of you had both of those right? Show of hands. Good. These also work for 3-dimensional objects. Let's say I have 2 cylinders. Pretend that looks like cylinders. And let's say this one started out 8 inches by 12 inches. And we expanded it, enlarged it so that this diameter is now 12 inches. What does this height have to be? Well, the diameter went from 8 inches to 12 inches. So 8 to 12. The height went from 12 inches to h. We cross multiply 12 times 12 is 144. Divide by 8, which is going to be 18. So that height is 18 inches. Now, since we've talked about three-dimensional objects being similar, we need to talk about some of the features of those two- and three-dimensional objects. What we've been comparing so far has been all lengths. What if I take a rectangle that is 2 inches by 3 inches, and I enlarge it so that this side is 6 inches? What's this side here going to be? Well, 2 becomes 6. 3 is going to become what? 6 times 3 is 18, divided by 2 makes 9 inches. That becomes 9 inches. What is the area of this? Well, 2 inches times 3 inches is 6 inches squared, correct? How about over here? Well, it'll be 6 inches times 9 inches is 54 inches squared. Let's look at the ratio of lengths here. 2 became 6. That can be reduced to 1/3. So a ratio of lengths could be 1 to 3 or 3 to 1 if you wrote the ratio the other way. Let's look at the ratio of areas. Six inches squared became 54 inches squared. Now that reduces, both divide, the inches squared cancel out. Both 6 and 54 can divide by 6 to give me a 1 and 9. So a 1 to 3 ratio of lengths gives us a 1 to 9 ratio of areas. Can you see a relationship between the ratio of lengths and the ratio of areas? If I square 1/3, what do I get? 1 squared is 1. 3 squared is 9. The ratio of areas is the square of the ratio of lengths. What that allows me to do is to take an odd shape I know I'm cheating by doing this, but let's say I have an odd shape and I'm going to enlarge it. So that this length here goes from being 6 inches to now being 8 inches. And over here, I knew the area was, let's see here. Let's say that I knew this area was 180 square inches. I can find the area of this piece. I start out with the ratio of lengths. The ratio of lengths is 6 to 8. Can that be reduced? I'm going to divide it by 2. It gives me a 3 to 4 ratio of lengths. So therefore, my ratio of areas is going to be found by taking that ratio of lengths, 3/4, or 3 to 4, and I'm going to square it. What is 3 squared? 3 squared is 9. What's 4 squared? 16. Good. So now 9 to 16 is my ratio of areas. I have the 180. Is that going to go on top or bottom? Is it from the smaller figure or the larger figure? It's from the smaller one, right? So it's going to go on top with the smaller numbers. So now we can cross multiply and divide. 16 times 180 divided by 9 is 320 square inches. So after being enlarged, that area has increased to 320 square inches. Any questions on that? Now again, this isn't restricted to a flat piece. It also applies to surface areas. If I have a weird shaped object, like that, my computer is really not liking this all. And we're going to enlarge it. Let's say this height here goes from being 10 inches to being 16 inches now. And I knew before that the surface area was 150 square inches. Let's look at the surface area of this thing. So I start out with my ratio of lengths. What's that ratio going to be? Did you give you a little time to finish the drawings? So what do we come up with for a ratio of lengths? 10 to 16, which reduces to 5 to 8. Very good. So then our ratio of areas is going to be what? Well, what do we do to the 5/8 or 5 to 8? We'll square it to give us 25 to 64. Very good. And of course, the 150 is the smaller number. So then we cross multiply and divide. 64 times 150 divided by 25 is what, 384 square inches of surface area, I believe. Does that work out? Okay. So if the ratio of areas is the square of the ratio of lengths, What do you think the ratio of volumes is going to end up being compared to the ratio of lengths? It's going to be cubed, exactly. So again, we're going to look at some weird shapes. So let's say for this one, this goes from being 3 inches up to being 5 inches. And this one here had a volume of, oh, let's say it's 81 inches cubed. What's the volume over here going to be? Well, we start out with our ratio of lengths, which is just the 3 to 5. To find the ratio of volumes from that, we would take the 3 to 5 and we would cube it. 3 cubed is 27. 5 cubed is 125. The 81 is from the smaller figure, so I'll plug that in on top. So our new volume is 125 times 81 divided by 27, which is 375 inches cubed. Any questions there? Okay, it's about break time. We're 1 minute early, so let's go ahead and take our break. It's 4:19. Let's start up again at 4. Okay, so what we're going to do now is we're going to shift gears a little bit, and we're going to look at representing information. Quite often in math, we have relationships that involve more than one number. Usually what we're going to limit ourselves to right now is sets of 2 numbers, but we might have a relationship where if the value of 3 is related to the value 5, it could be looking at a similar figure where it's 3 inches before and 5 inches after, or any sort of relationship like that. And we would list them like this in parentheses, and that is called an ordered pair. Usually, that first number is what we call an independent value. That means that's a value that we can choose and check to see what happens. Now, there's some relationship between these values. The second value is usually called a dependent value. Because if there is a relationship between these numbers, once you've selected this first number, the second number usually is determined by that relationship, depends upon that relationship. For example, one such relationship might be if we compare height and weight. So we can select people of different heights, but their height generally then will affect what their weight is. The taller they are, generally the more they're going to weigh. Notice it doesn't completely determine their weight, because there are people that are shorter than others that are still heavier than them. But it has an effect on them. It has a dependence on them. Well, one of the things we do with numbers to make them easier and quicker to reference is we like to represent them graphically. Now, we have represented values on a number line. Like if I wanted to represent the value 4, there are two ways we could represent that. One way that we did when we were dealing with integers and operations with integers is we used a vector. The vector for 4 looks like that. It's an arrow that starts at 0 and goes to 4. That's how we'd represent it if we wanted to be able to work with it. That's a working representation. It's useful. If we just want to represent the value itself and not use it for operations or anything else, we might just put a dot at 4. Now to go back to this ordered pair here, 3, 5, I want to represent both numbers, and I must represent that the 3 comes first and the 5 comes second. Doing that on a number line might be kind of tricky. I might have 3 and 5 and then maybe connect them with an arrow to show that the 3 is first and the 5 is second. But you can see how that would fill up that number line very quickly and get very cluttered. Well, about 2,500 years ago, a mathematician by the name of Rene Descartes came up with an idea to make this work. And what Descartes did was he said, we're going to take that number line just like we always do. And then we're going to add a second number line to it. Only the second number line is going to go vertically. It's going to go through the 0 of the first number line. Positive numbers are going to go up, and negative numbers are going to go down. And to represent a number like that, 3, 5, we're going to represent the 3 on what is the horizontal axis, which is that called the independent axis, or often referred to as the x-axis. So 3 would be right there. I'm going to change colors so it's more visible. 3 would be right there on the x-axis. And the 5 is going to be represented on the vertical axis, the dependent axis. Or sometimes referred to as the y-axis. Well, 5 is right here. Now, we technically wouldn't put marks there, but I'm marking them to show that's where these values are. To represent this point, then, that involves both numbers, we project them out to where they cross. That spot right there would actually be the point that would be put on this graph. And that represents the value 3, 5. Because the 3 is where if you trace it down to the x-axis or independent axis, and the 5 is where you would trace it over to that y-axis or dependent axis. Oops. Now on this graph, another very important spot is right in the center here. That center is the point 0, 0. It's the 0 point on both axes. It's also referred to as the origin, because that's where everything on this graph starts. If things start at 0, everything starts there. So if I put some points on here, what would that point be right there? What coordinate would it be? 7, 2. Perfect. 7 on the x-axis. We go side the x-axis first, and 2 on the y-axis. How about that point right there? Perfect. -3 on the x-axis, 4 on the y-axis. So -3, 4. How about this point? Six, -3, good. 6 on the x-axis, -3 on the y. So I'm going to assume that you guys can find those points on the graph at this point. Now you'll notice this section right here is where both x and y are positive. In real life, most of what we work with are positive numbers. So because of that, that section of the graph is referred to as the first quadrant, or just quadrant 1. From there, it's kind of arbitrary where they go. In math, just like in navigational directioning and stuff like that, we tend to go counterclockwise. So this would be quadrant 2, quadrant 3, and that is the Roman numeral 4, quadrant 4, down there. If we're representing real data, quite often one of the most common things we'll represent is changes over time, a relationship to time. In that case, time almost always goes on that independent or x-axis, because it's the elapsing of time that causes the other thing to happen, or allows the other thing to happen, not necessarily causing. So let's say you take a medication. Oops. So let's label this as milligrams of medication in the bloodstream. And this over here are time in hours. Notice the scales are not the same here. On the left side, each mark stands for 100 milligrams. On the bottom, each mark is a half hour. Let's say at time 0, the beginning, you start out with 800 milligrams in the bloodstream. And let's say that every hour, half of that medication leaves your bloodstream. So at 1 hour, you would be at 400. At 2 hours, you would be at 200. 3 hours, down to 100. 4 hours, down to 50, and so on. In most cases, we connect those points on the graph with a smooth curve. And what that curve represents is the values at different points in this relationship. We just had the values at 1 hour, 2 hour, 3 hour, 4 hour, and 5 hours. But what if we wanted to know the value right here? Well, if we trace that down, let's say that's 1 1/4 hour, 1.25 hours. If I trace that over here, that tells me the value. It looks like it's just over 300 milligrams still left in the bloodstream. I'd say 310 or 320. Let's say 320 milligrams. So you can very quickly get different values. If I wanted to know the value at 2.5 hours, well, here's 2.5 hours. I trace that up to the curve. Then I go over here. I can see it's between 100 and 200, a little bit closer to 200. That might be 170 or so. One of the weaknesses of these graphs is getting exact numbers. You can see here, since I am numbering by hundreds here, that is a 100 unit jump, a 100 milligram jump. It's really hard to find an exact number. If those were numbered by ones, it'd be a lot easier to get an exact or really close to an exact. But of course, that would make this graph like 7 pages tall as well. So every point on that line gives the values at some point in this relationship. Right here at half, let's say we wanted to go half an hour. Here's half an hour, you trace it up. Looks like we're looking something just a little over 500 milligrams in the bloodstream at a half an hour, and so on. So where does this graphing come into play? Well, I could have made a table of values here. Time in milligrams, 0 was 800, 1 was 400, 2 was 200, and so on. And I plotted those points on this graph. We didn't necessarily make the table, we just plotted the points as we went, and that's what we used to draw the curve. Well, sometimes our relationship is not given in just words like that, but it's given as an equation. We might have the equation 7 equals 3x plus 1. We've seen equations like that before. If we go to solve this, how would we go about solving this? Well, we would subtract 1. 6 equals 3x. Then we divide by 3. 2 equals x. But I might have an equation like 13 equals 3x plus 1. How would I solve this one? I would subtract 1. 12 equals 3x. And I would divide by 3. I get 4 equals x. You'll notice I took the exact same steps to solve that equation, but I had a different answer. Because this part of the equation was the same, but this over here was different. I could make several different related equations. I might have 16 equals 3x plus 1. To solve that, I'm subtracting 1, just as I did before. 15 equals 3x, and I'm dividing by 3, just as I did before. So 5 equals x. These are what we refer to as a family of equations. It's all the same on this side. This number here changes. So rather than just keep writing different values in here for that number, we represent it as y equals 3x plus 1. And that would represent all of the different equations in that family. The only way to show the solution for that family of equations is on a graph, because there's an infinite number of solutions. Every value I can think of for x, there's a value for y. And in this case, the other way around. Sometimes that isn't true. So the only way to represent all these solutions is to put them on a graph. The way I graph them is just like I did up here, is I get some of the values, I plot those points, and I use those points to figure out the shape of the graph. So how do I get those points? Well, just like I showed up there for the medication over time table, I make a data table. I pick values for x. Now for the medication over time table, I started at 0 because you can't have negative time. You can't go back in time from when you first put the stuff in the bloodstream. So we need to, but for here, we can have negative numbers. So to make sure that we get a good coverage across our graph, we might start out with something like a -2. If x is -2, we have to figure out what y is. Well, y is equal to 3 times x plus 1. So that'd be 3 times the -2 plus 1. 3 times -2 is -6. -6 plus 1 is -5. So that gives us the ordered pair when x is -2, y is -5. So that point would be right here. Now remember, we're plotting points. We always go side to side first. -2 is here. Then we go down to 5 to get to -5. So that's that point right there. We might try a different point. Let's try x equals 0. If x is 0, then y is going to be 3 times 0 plus 1. 3 times 0 is 0. 0 plus 1 is 1. So that gives us the ordered pair x is 0 when y is 1. So x is 0, y is 1. So 0 side to side, up 1 right there. That's 0, 1. Well, let's see what happens if x is 1. Y is going to be 3 times 1 plus 1. What's that come out to be? Yeah, 3 times 1 is 3, plus 1 is 4. So that becomes x is 1, y is 4. So x is 1, y is 4. Now, had I been careful making my graph, those points are on a straight line. Now, normally 3 points, I'd maybe try to get a 4th point at least to confirm that's a straight line. Not all points, not all graphs, not all equations are going to make a straight line. We can run into something like this. Y equals x squared plus 3x minus, actually, let me change that just a little bit. Let's go 4x minus 5. So we're going to try to graph this. We're going to make a table. I'm leaving a little bit more room because it's going to be a little bit more work to find y here. But I'm just going to pick some values for x. Let's say I pick x equals -2 again. I'm going to put -2 in over here for x to figure out what y has to be. So x squared becomes -2 squared. Notice I put that in parentheses. Many of your calculators, you're going to have to put it in parentheses to enter in your calculator so that it does it correctly. Plus 4x becomes 4 times -2 minus 5. Well, -2 squared, -2 times -2 is a positive 4, plus 4 times -2 is a -8, then minus 5. 4 plus a -8 is -4, minus 5 is -9. So that gives us the point -2, -9. So at -2, so we go over to -2, we go down to -9, right there. That's a point on the graph. Oh, let's see what happens at 0. So it's going to be 0 squared plus 4 times 0 minus 5. Well, that's easy. 0 squared is 0. 4 times 0 is 0. Minus 5 is negative 5. So when x is 0, y is negative 5. So 0, negative 5 is right there. Now it's tempting to just draw a line through those, but we can't be sure quite yet that that makes a straight line. So let's keep going, picking more numbers. Let's try x equals 1. So if x is 1, that's going to be 1 squared plus 4 times 1 minus 5. Well, 1 squared is 1. 4 times 1 is 4 minus 5. 1 plus 4 is 5 minus 5 is 0. So that's going to be 1, 0. So 1, 0 is right there. Now looking at that, it looks like this might not be a straight line. That looks kind of curved there. To figure out what's going on, let's try negative 1. If we knew what was going on right in here, it might help us figure out if that's a straight line. So let's try x equals negative 1. This is very common that you run into. You put a few points on there, and then you decide where you need to have more points so you can figure out what shape the graph is. So let's try x equals negative 1. So this is going to be negative 1 squared, come on now, plus 4 times negative 1 minus 5. Well, negative 1 squared is 1. 4 times negative 1 is negative 4 minus 5. Well, 1 plus negative 4 is negative 3 minus 5 is negative 8. So when x is negative 1, y is negative 8. So negative 1, negative 8, that's right here. This is definitely not a straight line. It's going to be a curve here. We need to figure out what it does over on this part of the graph. So let's pick like x is negative 3 and see what happens. So if x is negative 3, y is going to be, again, this is just coming from that equation, negative 3 squared plus 4 times negative 3 minus 5. Negative 3 squared is a positive 9. 4 times negative 3 is negative 12. And minus 5. Well, 4 plus negative 12 is negative 3, minus 5 is negative 8. So when x is negative 3, y is negative 8 again. So negative 3, negative 8 is right there. So this starts to go back up. And so we would keep picking points. So I'm going to pick another point here. I'm just going to keep going. I'm going to do x is negative 4 here to see what's happening over in this area. To keep going with it. Well, if x is negative 4, y will be negative 4 squared plus 4 times negative 4 minus 5. I'm going to leave it up to you at this point that you can figure out this value. That comes out to be negative 5. So if x is negative 4, y is negative 5. So x is negative 4, y is negative 5 is right there. You could maybe plot another point at x equals negative 5 and keep going. At x equals negative 5, y is going to be 0. And you'll see we get a curve like that. It's like a U shape. That is another common shape that we get along with our lines. The lesson I wanted to demonstrate here is we started out by just picking some points. But once we had those few points on the graph, we then used that information to say, okay, I need more points here and over here. So I'm going to use those values of x, see what I get for y, so I can plot more points and figure out what this graph looks like. Now, on top of the new quiz and the homework I'm going to give you for Thursday, there is going to be a worksheet that I'm going to post in Blackboard. I'm going to post it in Blackboard under course documents. Right along with, it's going to be right at the bottom of the class recordings. That worksheet will be in there. That's not going to be graded, but it's an activity that if you have it done, it'll help us with Thursday's class. Talking about what are some shortcuts we can use for graphing these equations. And all that worksheet is it's 10 equations that I want you to use a table like this and plot points and figure out what the graph is. So there is a new quiz. It's due for tomorrow. That'd be Wednesday at 11:59 p.m. And new homework that'll be due for class on Thursday. And then again, there is that worksheet. The worksheet is not graded, but it's, like I said, very helpful if you have that done for Thursday. Okay, you guys have a great day, and we'll see you on Thursday.